It is time for optimization problems part 2. All right. Obviously, you would have to look at part 1 of the video that I've already made and posted in order to understand anything in part 2. Here's how part 1 started off with this simple example about how to maximize the area of a rectangle if its perimeter has to be fixed at a certain number. All right. And then part 2, I wanted to look at some additional problems that are going to look different than the ones that I already showed you, but the methods are going to be the same throughout, okay? All right, so here's a problem I stumbled across, and maybe it's just me, but I actually thought that this one was kind of hard to read when I first saw it. All right, so I'll go ahead, I'll read it to you, and I'll even sketch out some examples just so that you can think a little bit about the way we're supposed to understand this information. Because like I said, maybe it's just me, and I'm definitely not the smartest person in the world, but I had a hard time thinking about how all this went together when I read it. All right, so I get humbled more and more every day, but here it goes. I'll read it to you. I'll show you some examples about how this might play out, and then we can use that to set up our equations and work the problem. Okay, so here goes. It says a rectangular poster must contain 162 square inches of printed space on it. Okay, there are margins at the top and bottom. Oh gosh, I'm sorry. Yeah, okay. No, I thought I'm having an off day. I'm sorry. The margins at the top and bottom of the poster must be 2 inches in width, and the margins at the left and right are to be 1 inch. So there's this printed space, and then there's margins at the top and bottom and left and right. What should the dimensions of the smallest poster like this be that is possible? Okay. All right. So anyway, all right, that's the statement. And apparently I'm still having trouble reading it as I read it to you just now, but like I said, I'm having an off day anyway. So here's how this might play out. I drew two, and these are not to scale, like very big disclaimer, not to scale. You see those pictures? I hope it's obvious to you that they're not to scale just when you look at them, but in case it's not, they are definitely not to scale. But they're able to give you an idea of the way that this plays out when we read this example. Okay, so here is a poster. Okay, and it has 162 square inches of printed space on it, like that. Okay, it has a margin at the top and the bottom and the left and the right. Okay, it said, now here's just one possibility. It's 2 inches this way, 81 inches that way. That would have 162 square inches of printed space on it. All right. Now, if the margins at the left and right are both an inch, that means the width of the poster would be 81 plus 1 plus 1, which is 83. And if the margins at the top and the bottom are each 2 inches, then that means the height of the poster would be 2 plus 2 plus 2, okay, which would be 6, okay? So with the dimensions of the printed space plus the margins factored into it, this poster is 83 inches by 6 inches, okay? The total poster size is 83 times 6, or 498 square inches. All right, that's one way it can play out. That's one way that you could have a poster with this much printed space on it and with the margins that are described. But there's lots of other ways, okay? It's just like my first example in my last video. There are lots of ways you can have a rectangle with a perimeter of 20, right? Lots of different ways. Lots of different widths and lengths are possible. All right, so again, for this problem, another way that this could happen is the printed space could be 6 inches by 27 inches. Okay, so 6 times 27 that's still 162. So it still has the same amount of printed space on it, 6 by 27. But if the margins on the right and the left are each an inch, then that means the width of the poster is 27 plus 1 plus 1, and that's 29 inches. And if the margins at the top and the bottom are each 2 inches, then that means that the height of the poster is 6 plus 2 plus 2, and that's 10. All right. So such a poster like this is 29 by 10 or 290 square inches. Now, look how vastly different the sizes of these posters are going to be. They both have the same amount of printed space on them. They both have the same margins, but then this one is significantly bigger than that one. All right. So just, let that sink in. That gives you, hopefully, a little bit of perspective on how to read the question. And you can see that, just maybe surprisingly, even though the same printed areas on each poster and the same margins, the overall sizes, the total areas are much different. This one's much bigger than that one. Okay? All right. Now, thinking about reading this again, I want to pose this in a way that we can use calculus to solve it. I guess I could sift through more possibilities, and maybe I would find the one that is truly the minimum size poster that fits the conditions in the problem. But I won't do that. I'm obligated to show you the calculus, so here it goes. Here's the math. Here's the calculus. This is not just math, but we're using calculus, in fact, to do it. I want to minimize the area of the poster, subject to the constraint being that the printed space in here, okay, so this amount of space is going to have some kind of print or writing on it. That's got to be 162 square inches. Now, what's the overall area of the poster? That's this. When I put A for area, that's the area of the entire poster itself, margins and all. Well, so here's how I compose this problem. I said, well, let's call for this printed space in here. Let's say it's x by y. All right? And x times y has got to be 162 because it says the printed space must be 162 square inches. Now, the overall size of the poster, remember, we got 1 inch margins on the left and right. That's going to be y plus 1 plus 1. That's y plus 2 for the total width. And remember, we have 2 inch margins on the top and bottom. So the height of the poster is x plus 2 plus 2. That's x plus 4. So we want to minimize the area of the poster subject to the constraint of the amount of printed space in it. All right. Now, do you remember from the other video how we took it from here? The way that we did it from this point is we use the constraint if we formulated the constraint separately from what we were minimizing, and reduce this function to be a function of just one variable. As it is, this is a function of x and it's a function of y. It's a function of this and that. I want it to be just a function of either x or y alone. So we'll take this one and we'll work that around to this effect. We'll say, all right, y is 162 over x, and then we could take that and we could put that in right there. And that would reduce it to being just a function of x. If we do that, I'm going to get area is x plus 4 times y, but y will be substituted as 162 over x plus 2. Now that reduces the area, the overall area of the poster, which we're trying to minimize, make it as small as it can be, to a function of just x. All right, so what do I do with this now? I want to minimize this, okay? And that will involve finding the derivative and setting it equal to 0 and solving it. All right, so in order for me to do that, I think it would be best to multiply all this together. So x times 162 over x, that's going to be just 162. And then I'll get 2x. Okay, so 162 and 4, so 648 over x. Okay, so, and then 8. All right, 4 times 2. Okay, and I'll go ahead, I'll add some terms. I'll get 170 right there. 162 and 8 plus 2x plus 648 over x. Okay, so that's reduced a little bit in a way that I think will make the derivative easier to get. So a prime, the derivative of this, which my goal is to set equal to 0, will be 2 minus 648 over x squared. Okay, and then I'll set that equal to 0, right? And then I'll get like so. Okay, and then I'll get like so. Right? Okay, and then 324, I believe, is a perfect square root. I sure hope it is. And it is 18 squared. Okay, so x is 18. And we were doing all the measurements here in inches, so 18 inches. And so what's that mean? It means that this is going to be 18 right there. All right. Okay. Now I'll go ahead and give all the dimensions. All right, all the dimensions. So here's what it'd be. Here's what I found out. But this is 18 inches. So the height of the printed area needs to be 18. What's the width of the printed area? Well, the total printed area is 162 square inches. So if I take 162 and I divide by 18, then I'll get that it's 9. So this is 9 inches. Okay? So that printed area, the area of the poster minus the margins that has print on it, is 18 by 9. What about the poster itself? Well, so, okay, this is 9, and you got the 2-inch margins on each side. So that's going to be 9, and then, oh, wait. Yeah, 9 plus 2, so that will be 11 inches. Okay, because we got 1-inch margins this way, so 9, 10, 11. That's why it's y plus 2. And then over here, this size, the height of the poster, is x, or 18 plus 4, so that's 22 inches. All right. So just depending on what aspect of the dimensions it's asking you for, you could say, all right, we need the printed portion of the poster to be 18 by 9. Or we need the overall size of the poster to be 22 by 11. Okay, it just depends on exactly what about this it's asking you. But nonetheless, like that number, like no matter how you put it up here, that's as small as the poster is going to get and have the margins as desired in the printed space as desired. Okay. All right, so that's that one. Let's do another one. Very much different. Okay. So I'll have a look at this one. So imagine this. There are 2 factories 14 miles apart. There's a power station 20 miles that way. And there's like this power transmission line. Okay? And the power transmission line has to split at some point to go to each factory. All right, so that's the question. From that, I'm wondering, where should the power line split to minimize the total length of the power line? So in other words, where should this point be? You can imagine it moving at different places, like maybe the split should occur real close to the power station. Maybe it should occur a lot closer to where the factories are, okay? Given that we want to deliver power from the power stations to the factories. Now, I wanted to describe it just like that and say, well, that's how, like, maybe the question might be given to us, and they're saying that here's where everything is. In order for us to do anything with it, we need variables, numbers, equations, and so on. So I might put it like this, okay? So as my diagram puts like this split like right in the middle of those, then I might say that, okay, well, so they're equally distant from each other. So maybe one of them is at 7, and then the other one is at -7, okay? And then I'm wondering where this point should be, which is the split, so I'll put 0 and y, being that I'm putting it as some point on the y-axis. And then the power station itself was like 20 miles that way, so I'll put that as 0 and 20. So I'll, in order to make it such that it's amenable to doing math, I'll put it like this. So there's the transmission line like so, and like so, and like so. And that maps my original diagram onto a graph where I have an x and a y-axis. Okay? Now, still, like, these are 14 miles apart, and that their power station is 20 miles that way. And the split occurs where? Where does the split occur so I can minimize the total length of line, power line, transmission line, that I'm running from here to there and there? Okay? All right. So I want to do this. Minimize the length of the power line, which on my diagram is written in red. All right. So could we get a formula that measures the length of the line? That would be the obvious place to begin. So, like, let's take this one. How much line is there right there? Well, there's a triangle, and that distance is 7 miles, and this distance is y miles. So, like, this length of line right there is the square root of y squared plus 49, being that that length is the hypotenuse of a right triangle. Now, we also have that same amount of line over here, okay? And what about this line right there? How much line is there? Well, this point's 20 units this way, and this point's y units this way. So this is 20 minus y. So let's say D, the total distance or length of, how about, let's call it L. I like L better. So let's say L, the total length of line needed to power the 2 factories from the power station is going to be this. It will be 20 minus y, okay, plus 2 root y squared plus 49. Okay. All right. Now, what do we do with that? That measures how much line it's going to take, all based on where that point is, where the split occurs. It occurs at point y on the y-axis. This is a function of y. Now, real quick though, in some problems, like I have to write the constraint separately, and then I use the constraint to substitute into what I'm minimizing or maximizing to reduce it to just one variable. Here I took my area, which I wanted to minimize. It was a function of x and y. Through the constraint, I reduced it to be just a function of x. In this problem, there's no separate constraint to write down. When I write an equation for the length of power line, that's the thing I'm trying to minimize, it's already just a function of one variable. So I don't have to do anything separate to it. I can just like take this the way that it is, and I could say, well, I wonder what's the L prime, the derivative of that, what's it going to take for that to be 0? Okay, that will take me to the answer to my question. All right, so let's do this. Let's find L prime at this point. I'll get -1 from this, plus 2. My derivative of root y squared plus 49. That will be 1/2 y squared plus 49 -1/2 times 2y. Okay, so doing a little simplifying, I'll get L prime to be -1. I'll get some canceling there. Let's do like this. I'm going to say we'll get 2y remaining here with the 2's canceling. And I'll get root y squared plus 49 down there. Okay, so there's my derivative of the equation, the function, that gives you the length of power line in our schematic. I said equal to 0. If I do that, I'll get root y squared plus 49 equals 2y, which I just get from a little bit of cross multiplying. Okay. Then from here, as a means to solving the equation, I'll square both sides. And so I'll get y squared plus 49, squaring this root, is 4y squared. I'll get 49 is 3y squared. Okay. Or dividing by 3 and taking the root, I'll get y is equal to 7 over root 3. Okay, so that's where that point should be. I'll write my final answer up on my diagram. You could say like, well, the power line needs to split at 7 over root 3 miles that way. You could say this point right there on the y-axis needs to be 7 over root 3. If you put it there, you'll be running the least amount of transmission line possible. All right? You can't get away with any less than if that's where you put the split, at 7 over root 3 on the vertical axis. Okay. But I think at this point, now that we've seen a few examples, maybe the algebra is starting to look familiar. We're seeing a lot of the same techniques to solve these. Anyway, so that's what I get. I want to talk about a variation of this problem real quick, where suppose that somebody tells you, I don't know where that point's going to be either, but it's going to be fixed. And I don't want to say where these points are, but they're going to be fixed. What's it mean if I say this point where the power station is fixed? Well, it means that h is a constant. Okay? And what's it mean if I say this point and that point, the location of the factories are fixed? Well, it means x and negative x are also constants. And this is the point again where I'm moving around. Now, so if you happen to see the problem this way, it's just like this one. It's just that I'm not saying that the power station's at the 20-mile mark on the y-axis, or the factories are at the 7-mile marks on the x-axis. It might be that sometimes you have to do the math with incomplete information. You know a certain number is a constant, you just don't know what it is. Now, can't we still do it the same way though? Even though we have less information to work with. H is a constant, x a constant, and x is a constant. Okay? So, that means that the total length of transmission line is going to be h minus y plus 2 root x squared plus y squared. Okay. Now this is a function of, well, what? What do you think it's a function of? What's the variable? Well, h is a constant. This point is fixed. It's not going to be anywhere else but then at point h on the y-axis. X is a constant. These points are fixed. They're not going to be anywhere but point x and point negative x. Y, we're trying to figure out where the split should be. Find the location of this point where the line splits so that the total distance in red is a minimum. So this is going to be a function of y. So now I'm gonna let you do this one because I think at this point it's similar enough to the others. But we're going to look at h like that's a constant. And you know what we do with constants in calculus. We have certain rules, such as the derivative of a constant is 0 and so on. And x right there is a constant. All right? So again, like you know what we would do with constants in calculus. There are certain rules that are appropriate. So what I'd like you to do is find L prime and set it equal to 0 and solve it. And tell me where this point should be. Okay? All right. So I'll leave that to you. As with anything, if you just can't get it to work, if you get stuck, then go ahead and ask me about it. I'll fill in the gaps for you. I just wanted to leave something for you to try to do by yourself. Okay. So let's do one more problem. All right. So this one a little bit more abstract than the others, but I think you can still imagine it. Okay. Imagine that this point is fixed at 0 and 2, and this point is fixed at 4 and 1. And this point is variable, like I could move this point around. Can you imagine that if I move this point around at various spots between 0 and 4, that this angle might get bigger or smaller? Okay, so you can probably imagine that. There is a point where you could put this spot that makes this angle as big as it can possibly be. All right? So say I tell you that. You can imagine it might differ as I move it around, that angle might get bigger or smaller. But there's a point where it will be its greatest. All right. So how do we answer that? Now, if it's like the others, we need a formula that expresses theta in terms of something else. Like if I want to minimize the length of the power transmission line, I need to put that length as a function of, other variables that are involved. Okay? So in this case, I'll say, well, I'll put theta as a function of something. So here's how I'll do it. I'll say, well, look, say this is angle B, and say this is angle A. Then I can relate these things together. Angle A plus angle B plus theta is 180 degrees. That's true. Okay? So that says I can put theta in terms of other elements of this picture as 180 degrees minus A minus B. Okay. All right. What can you tell me about angle A? Well, for angle A, there's this triangle right here, and it's a right triangle. And this side's 2, and this side's x. So I could say that angle A is tangent inverse 2 over x. All right. And what about angle B over here? Well, so it's like kind of construct around it like that. Angle B, so this triangle, so that's 4. And how big is this side? Well, this is at point X, and how far over is this? Oh, that's not 4. I'm sorry. That's 1. Okay. How far over is this? That's 4. So what's this, the base of that triangle? 4 take away X. All right. So I can find angle B. It's going to be tangent inverse 1 over 4 minus x. Okay, so that will get me theta to be a function of the location of that point. All right, so let's put these together with this. Okay, all right, so theta is equal to 180 degrees minus A, tangent inverse of 2 over x, minus B, which is tangent inverse 1 over 4 minus x. All right, and this is the thing I want to maximize. Through this equation, I can find out the biggest that angle could be based on its various locations that I could put that point. Okay, what will that involve? All right, well, that will involve finding theta prime, the derivative. Okay, so I might, let's do this. Let's say if my first step I'll get negative. What's the derivative of tangent inverse? The derivative of tangent inverse of u, so say that's my u, is 1 over 1 plus u squared, so in my case 2 over x, times u prime, which is going to be negative 2 over x squared. Okay? And then minus, same thing here. I'm going to get 1 over 1 plus u squared times u prime. What's the derivative of 1 over 4 minus x? It turns out that's 1 over 4 minus x squared. Okay, and that's just because we could think of this part right here as 4 minus x to the negative 1 power and use the chain rule on it, and that's what you'll get. Okay, so, all right, let's do a little more simplifying. That makes theta prime equal to, like, again, with some simplifying. For this first one, doing algebra and so on that we probably know how to do, but if you need to ask about it, you can. You'll get 2 over x squared plus 4. And then for this other one, we'll get, say if we distribute and so on, we'll get 1 over, let's say I distribute and I do all my squaring and canceling and everything, I'll get x squared minus 8x plus 17. Okay, and that's about as simple as theta prime is going to get. Now, if I set that to 0, then I'll move this over there to solve it, and I'll get like this, 2 over x squared plus 4 equals 1 over x squared minus 8x plus 17. Okay, so that's where I get at that point. Now, if I do some cross multiplying and I combine like terms and I do all that typical kind of stuff that we do, you know, when we solve equations like this, so cross multiply, combine like terms, rearrange, then this is the equation that I get. X squared minus 16x plus 30 equals 0. And we can use the quadratic formula to solve that. All right, so here goes. X is equal to, let's do 16 plus or minus root, and I need to do 16 squared minus 4 times 30. So 16 squared minus 4 times 30, so 136 over 2. And then I'll reduce that a little bit. 136, that divides by, it's 4 times 34. So this is going to be 16 plus or minus 2 root 34 over 2. And then I'll divide by 2, and I think I'll get my solution. 8 plus or minus root 34. Okay, so I get 2 answers. Now, you'd think there'd only be like one spot where you'd put that, where the angle would be as big as possible. But then that's 2 numbers. So I'll get you each of those numbers. We'll just have to see. For example, what's 8 plus root 34? Turns out that is equal to about 13.8. All right, and so I get 13.8. Well, that's, you know, that can't be the answer, because this point is only 4 spaces to the right. I can't put it at 13. I mean, that wouldn't have any meaning here. I'm saying we're putting that point, you know, somewhere between these 2 points. So it's not that one. And then 8 minus root 34. Let's see what that is. So that number turns out to be about 2.16. Okay. So that's more like it, 2.16. So let's give our answer this way. We should put this point right there at, let's just say 8 minus root 34 and 0. So there on the x-axis, which amounts to putting it at about 2.16, right there in the middle between 4 and 0, between these. Now the other component of the question is, well, sure, that will get you this angle to be as big as possible, but how big will it be? Okay, well, let's see, max angle. What is, in fact, the biggest that angle is going to be? Well, look at it like this. So I know the x that's going to get me the biggest angle. Here's the equation that tells me what that angle is going to be. It says theta, see this angle right here? It's going to be 180 degrees minus tangent inverse minus tangent inverse. So I've got that number right here. That might seem like a lot to put in the calculator, but I could do like this. So I take 180 minus tangent inverse 2 over, now there, like I'm using a feature of my calculator, probably yours too, where I can recall a number that I just had. So I'm recalling the 2.169, the 8 minus root 34, and then minus again, tangent inverse, 1 over 4 minus x, which I do like that, and it will tell me the biggest possible value that angle is going to take if we put it here. And so that turns out to be 108.68. So let's say the max angle possible in this scenario is 108.68, and I did all that math in degrees. Okay, so that's the location of the point to give maximum size of the angle, and this is the maximum size of the angle.